today we're going to talk about natural transformations. Natural transformations are like morphisms between functors. And as category theorists, of course, we like morphisms. Morphisms are practically the entire point of category theory. Is that true? Never mind, that's what I'm going to say for now. Because they're the things that we use to express structure. We start with objects, and then in our category we have morphisms that enable us to talk about different kinds of sameness between objects other than just equality, and other kinds of more exciting structures. So when we're thinking about categories, we then think about morphisms between categories. And those, as we know, are functors. And then we might start thinking about morphisms between functors. And those are natural transformations. So here's the definition. A natural transformation, well, first of all, we have to decide where a natural transformation is allowed to live. Given categories and functors like this, so we've got categories C and D, and we've got a functor going from C to D, and another functor going from C to D. So they really have to start and finish in the same place, otherwise we're not allowed to even think about having a natural transformation there. Oh, now I can't make this grammatically work. It's going to be a dynamic definition or something. A natural transformation, the natural transformation is going to live there. A natural transformation, natural transformation alpha. Do you know what? Someone in my audience is eating chocolate cake during this lecture. Do you think that's acceptable? Okay, a natural transformation alpha is given by, now what we have to have, and I do remember when I first saw the definition of natural transformation, I thought it was very, very strange. What we have to have is for every object in C, a morphism in D. For all objects X in C, a morphism alpha sub X that goes from f of X to g of X. And that's going to be called, we're going to refer to that in general as a component of this natural transformation. So this is called the component of alpha at X. And of course it's not just any old collection of morphisms like that. There has to be some axiom satisfying naturality. What does naturality say? Well, it says, given any morphism in C, something has to be true over here. So we're talking about categories and functors, so we're probably thinking about objects and morphisms. And the point is that a natural transformation says, for every object in C, we get something over here, and for every morphism in C, we get something else over here. So for the morphisms, what is it that we get over there? So all morphisms F going from X to Y in C, the following diagram commutes. Hopefully you can still see it at the bottom of the board here. So what can we do? There are two possible things we can do. We can either start from f of X, use our natural transformation to get to g of X, and then do g of our morphism to get ourselves to g of Y. Or alternatively, we can do f of F down here. Whoops, that takes us to f of Y. And then we can do our component of the natural transformation afterwards, alpha of Y. So that, rather small, this is really the key thing, and I don't know what I can do to make it more key, given that I've squished it at the bottom of the board here. Maybe I'll just draw a big red circle around it. That is the naturality square. So these are the, and there's one of them for every morphism in C, so these are the naturality squares. And these are really the things that make this entire definition tick. So next time, probably, we'll look at how we can compose natural transformations, because I just said that there was some kind of morphism between functors. And if they are kind of morphism between functors, then you really want to be able to compose them. But before I do that, I want to try and shed a little bit of light on what this definition is about, which will make sense to anybody who's ever seen the notion of homotopy. So let's just have a sort of thought experiment about homotopy. If you think about spaces x and y and continuous maps between them f and g, we know what, now I've made this diagram look an awful lot like the other one for a reason, we know what the notion of a homotopy from f to g is. Because what it is a continuous map from x cross I to y, such that when this is 0 you get f and when this is 1 you get g. But what that in particular gives you is that if you fix an object of x, right, then what you're going to get as you vary yourself along this I part is a path from f of x to g of x in y. So for all, what you get here is that if you fix x, we get h of x blank, which is a path from f of x to g of x. And this is really a bit like what's going on here. For every x in the source part, we have the categorical notion of path from f of x to g of x, and the categorical notion of path in this case is just a morphism going from there to there. And so what's this commuting naturality condition saying? Well, let's imagine that we're looking at a homotopy between two paths in space. So here's a space, and here's one path, maybe that's f, and here's another path, and maybe that's g. And a homotopy between them says for every point t somewhere along this path, we're going to get some path that takes us from one place to the other. And for every other point, t prime, we're also going to have a path from f of t prime to g of t prime. So you've got this kind of square, right? And given that this is supposed to be like the component of the natural transformation in one place, and this is supposed to be like the component of the natural transformation in the other place, you sort of think, well, this naturality square somehow ought to correspond to this square commuting. Now, what does it mean for a square of paths to commute in a space? Thought experiment, thought experiment. Well, it sort of ought to mean that there isn't some great gaping hole in the middle here. If there's a great gaping hole here, then there isn't any sense in which this path is the same as this path. But if there's no great gaping hole in the middle, then there is a sense in which this path is the same as this path. And if you think about it, that's kind of what it means for this path to be homotopic to this one, right? You can get your way all the way down here without running into some enormous hole. So that's sort of like what this naturality condition is saying. So you might say to ourselves, well, is there some way of getting at natural transformations in this way? And the answer is yes, there is. I won't have time to go into it this time, but you could look at a natural transformation as being a functor from C cross I to D, where this I has to be a bit like the categorical version of this I. Now what's this I up here? It's the topological interval. So this I ought to be the categorical interval, whatever that is. Well, what do you think the categorical interval is? The categorical interval is a very small category that consists of an object at the beginning, an object at the end, and a morphism going in between them. So an exercise before next time is to work out what part of this definition gives the naturality condition here. Today we're going to talk about composing natural transformations. Last time we saw that natural transformations are some kind of morphism between functors, and so if they are some kind of morphism, then we really ought to be able to compose them, otherwise it would be stupid to think of them as being morphisms. But let's just recall what the definition of natural transformation is. we're allowed to have a natural transformation in this situation when we've got a category C and a category D and two functors that we could call parallel because they've got the same source and target, even though they're not really very parallel on this blackboard. So they go like that, and this natural transformation is allowed to go in between them. We can't have a natural transformation between two functors where the source and target are the same. So a natural transformation is given by, for every object in C, a morphism in D, and for every morphism in C, this naturality square has to commute. Okay? So fundamentally, we've got a bunch of morphisms in D going from f of x to g of x. So hopefully it's now obvious to you how we can compose natural transformations. So let's just draw a little picture over here so that I don't run out of space. Composition, if we've got, we're still going to just have two categories like this. If we've got a functor f, a functor g, and a functor h, and a natural transformation alpha like this, and a natural transformation beta like that, I'm now going in completely the opposite direction across the board from my co-Capster colleague in his string diagram lecture. So I'm going down the board like this. What can we possibly do to compose these things? So the composite beta composed with alpha. Well, how do we define a natural transformation? First of all, we define its components. So we've got to have a component at x that goes from, well, this is a source, okay, beta composed with f is going to go from f to g, h. So this is beta composed with alpha. So it's got to go, the component has to go from f of x to h of x. How could we possibly do that? Okay, well look. If we stick g of x in the middle, we've got a component of alpha that goes from f of x to g of x, and we've got a component of beta that goes from g of x to h of x. So miraculously, we've now got a component that goes all the way from f of x to h of x. Fine. So what do we have to do now? We have to check that it's really natural, which means that for every morphism in C, this kind of square has to commute. So what's that diagram going to look like? Here's the naturality square. I could have just drawn it under there, but it might have been confusing. Right. So here's the component of beta composed with alpha at x, and here's the component at y. So here's f of f, and here's h of f, and this is the square that has to commute. But look, there's this great big gap in the middle of the square that's just crying out to be filled in. So let's go ahead and fill it in with a g of f, and bingo, this diagram commutes because of naturality of alpha, and this square commutes because of naturality of beta, so the entire thing commutes. So this really is natural. It's at this point that we start using the word natural in an extremely technical sense, rather than just natural. It's actually natural. Right. So we have a way of composing these things. It's going to be associative, because composition just happens by composing morphisms in the category, and it's also going to have a unit, identity. In identity 1 on f, which goes from f to f, well, what's it going to do? It's going to have components that have to go from f of x to f of x. So, of course, it's just going to be, the components are going to be the identity in the category D. So the identity has components, the identity on, let's get rid of that for a second, the identity on f of x, which goes from f of x to f of x. So what have we done? I hope you all feel highly confident that you can go away and check that this forms a category. A category, oh, thank you. This forms a category of what? We have defined a whole category of things between C and D. So this is the functor category. The objects are functors from C to D, and the morphisms are natural transformations in between them. Good. Now you might have noticed that there's another possible way of composing natural transformations. Because look, we can compose functors in this direction along the board. So what happens to the natural transformations if we do functors along this direction? So this is a whole new thing. Also, now let's get rid of something, maybe all of it. We can compose horizontally in this direction. Now this is a bit of a funny looking composition, and it's usually written as star. So this happens if we've got three categories, and this goes from F to G, and maybe this goes from F prime to G prime. And so what are we expecting? We're expecting, well, we can compose the functors along the top, so we get F prime composed with F. We can compose the functors along the bottom, so we get G prime composed with G. And so we expect something that lives in there, and we're going to call it beta star alpha to show it's different from beta round circle alpha. How are we going to define it? We need to define it on components. Well, beta star alpha has to have a component of x. Now where does it have to go? It has to go from f primed f of x to g primed g of x. Now let's think about this. F primed f of x is just f primed of f of x. Now we've got a map from f of x to g of x, which is alpha x. So if we do f primed on alpha of x, that takes us to f primed of g of x, right? Now this is g primed of g of x, and we've got a map from f primed of anything to g primed of the same thing. And that's the component of beta. So if we do beta at the object g of x, that sends us from f primed of g of x to g primed of g of x. Hurrah! We got there. But you might have noticed there was another way of doing it as well. Because instead of doing f primed on alpha of x, we could have regarded f of x as one thing. Maybe I'll turn this into something a bit more sensible looking, f primed f of x. So we could regard the f of x as one thing, and we could do the component of beta at f of x. And that will take us to g primed of f of x. And now we can use g primed of alpha and get us back to here, g primed of alpha at x, which gets us to g primed of g of x. Is that a problem that we had two different ways of getting there? Let's stare at this for a second. Oh look! It's a naturality square for something, I hope. Hopefully it's a naturality square for beta. Because look, if we sort of turn ourselves this way up a bit, this is a component of beta, and this is a component of beta. And we're regarding alpha x as being a morphism from f of x to g of x. So remember, we had to have down one side the functor applied to morphism, down the other side the other functor applied to morphism. Ah! And so this is a naturality square for beta. So in fact, these two ways of going around the square are the same, and give us only one way of defining horizontal composition of the natural transformations. Now next time, or perhaps in between, you can see if you can show that that really is natural, and next time we'll show how to talk about the interaction between the two kinds of composition that we just defined. Today we're going to talk about the middle four interchange law. Now last time we talked about natural transformations, and we defined two kinds of composition for them. We defined horizontal composition and vertical composition. Now, the middle four interchange law governs the interaction between the horizontal and the vertical composition. But before we look at that, I want to talk a bit more about this horizontal composition that we defined and see what's really going on. tell you the whole story last time. Now remember, this is how we define horizontal composition. We're starting with a configuration where we've got two natural transformations, alpha and beta, that are kind of side by side like this, and the aim is to produce a natural transformation that goes from the composite along the top to the composite along the bottom. And this is the formula we have. Remember that there were two ways of doing it, but they were both the same because of the naturality of beta. Now, let's just try a little experiment here. What happens if one of these things was the identity? So let's try putting beta to be the identity. So H equals K, and let's put beta to be the identity on K. Then what happens to this formula? So we get beta is the identity on H. So that's the identity on H star alpha. Its component at X. Well, let's just plug it into this formula. Up here, we get just the same H of alpha of X. And here, what have we got? We've got the identity natural transformation. And the identity natural transformation, remember, it has every component is the identity. So every component of that is the identity. Oh look, we just composed something with the identity. Nothing happens. Right, so that's what we've got there. And because it looks like H, it's just H of alpha, we sometimes write this natural transformation as just H alpha. And we sometimes draw it like this. Alpha goes from F to G, and then it's just got a flat bit on the end, which is H. So now let's try making this side a flat bit. So now let's put F equals G, and put alpha to be the identity on F. So now we're looking at a flat bit over here. We've got a beta here, and we've just got the identity on F over here. So let's see. Beta starred with the identity on F, its component at X. Well, now let's plug it into here. This is still going from H to K. So what we're going to have here is we've got beta at the component f of x. So we've got beta at the component f of x composed with k of the identity. Now k of the identity is of course just the identity, so when we compose it with that, that's all we get. Right? So because this looks like beta with an f on it, we sometimes write this as beta with a functor f on the right hand side. This one is a bit more straightforward. This one looks a bit funny, and you have to remember that what this means is its component at x is the component of beta at f of x. So it's like we've defined two little fishes, one that's swimming in this direction and one that's swimming in this direction. And now if you look really carefully, the general definition we made of horizontal composition is really the composite of a fish swimming in one direction followed by a fish swimming in the other direction. You see, we've got h of alpha first and we've got beta of g afterwards. So what we've really done here is, so if this is the first definition and this is the second definition, our first definition of horizontal composition really said do alpha with an h stuck onto it first and then do beta with a g stuck onto it afterwards and compose those two things vertically. Okay? Now, the second definition, what did the second definition say? It said do it the other way around. It said do beta with an f stuck onto it first and then do alpha with a k stuck onto it afterwards and now compose them vertically. So this was the second definition that we gave that corresponds to this one here. And naturality says that those two definitions are the same. So these are equal by naturality. So that's what we secretly made use of when we made this definition of horizontal composition. And now it should become completely obvious that the middle four interchange law is going to hold. Of course, it's not going to be obvious when I haven't told you what it's supposed to be. So let me now tell you what the middle four interchange law says. It says that supposing you've got four, that's why it's middle four natural transformations in this configuration here, alpha, beta, gamma, delta. Now you'll notice that there are two possible ways you could compose up this diagram. You could either do the horizontal bit first. You could do alpha composed with gamma horizontally and beta composed with delta horizontally. So let's see, what does that say? You've got alpha composed with gamma horizontally, and then afterwards you're going to do
compose with beta horizontally. So this is sort of do this horizontal part and do this horizontal part and then compose them vertically afterwards. Or you could alternatively do beta compose with alpha vertically, followed by horizontally delta composed with gamma. Let's see, have I got that right? So you're doing, yeah, so this is the left-hand part. It's always a bit confusing because we're writing everything backwards. Okay, so these are the two possible ways of doing it. And this one is like saying, do the vertical parts on each side and then stick them together horizontally afterwards. Now the point is that these two things are supposed to be the same. So this, which I'm now going to write in the middle of the board, is the middle for interchange law. The middle for, that's the middle for interchange law, is this. So why is it true? Well, you can sit down and write out all those components if you really wanted to and check that it's true by naturality. However, I've drawn these nice little pictures, at least I think they're nice little pictures, over here. So I'm going to use those nice little pictures to show it's true instead. I don't need this junk anymore. So what's it saying here? It's saying, do the horizontal composite and this horizontal composite. So let's say that we're writing this horizontal composite like this in the first way. So we're doing this horizontal composite. That's alpha, this is alpha, beta, gamma, delta. So we're doing alpha, gamma, and then we're doing beta, delta. Okay? But oh look, this naturality thing says that we can switch round the two little fishes in the middle so that they're both pointing the same way. So that's the same as we leave the top and bottom the same, but now we switch around the two little fishes in the middle so that they're swimming in the opposite directions that they used to be. You can only switch them around if there are two of them, of course. But what's this? That's the vertical composite of alpha and gamma. And this is, so that's alpha and gamma. And this is the vertical composite of beta and delta. And now we've got two little sort of composite fishes swimming in opposite directions. So we know that what we've effectively done is we've composed them horizontally. So you'll notice that actually the only thing we used here was the fact that we can swap these two little fishes in opposite directions, and that shows that the middle for interchange law holds. That's not completely rigorous proof, but as I said, you could sit down and write down all the components if you really wanted to. I don't really want to, so I'll leave that to you. Next time, what we'll show is that this is one of the key axioms that characterizes a two-category. And what we're going to show is that categories, functors, and natural transformations form a two-category. Now, this is really a continuation of Natural Transformations 3, because there were a few things that I decided in all honesty I really ought to say, and the sharp-eyed among you have probably been asking yourselves these questions already. The first comment I want to make, it's all about this way of defining horizontal composition of natural transformations by these little fishes swimming in opposite directions. The first thing I want to mention is that this is often referred to generally as whiskering, because you can sort of see that you've put some whiskers on the edges of things. And what I really needed to say was something about this supposed proof I had of showing that the middle for interchange law holds using the process of having these fishes swimming in the opposite directions. So if we just look for a second at what I did, I had these fishes all swimming in opposite directions. Then I used this naturality of beta, of something in the middle here anyway, to swap these two middle fishes around so that they were then swimming in opposite directions. So first they were going like this, and now they're going to go like this. And then I somehow compiled these top two fishes that were swimming in the same direction, and these two bottom fishes that were swimming in the same direction. And here, you might want to ask yourself a question about why that was really true. And it's quite interesting, actually. So let's have a look at this. We've got an alpha with something on the end, which I'll call, what should I call it? I'll call it H. And here we've got a beta with an H on the end. And the components of H alpha are just H of alpha of x, and the components of H beta are just H of beta of x. And so what we're going to do now is we're going to do vertical composition of these two natural transformations. And how do you do vertical composition of natural transformation? Well, you just go right ahead and compose. You just go right ahead and compose the components. So H of beta composed with H of alpha vertically has at x the component H of beta of x composed with H of alpha of x. Okay? But we know by functoriality that that's the same as H of beta of x composed with alpha of x. And look, this is therefore the vertical composite alpha followed by beta with an H stuck on the end. So actually this part here follows from the functoriality of this. Okay, so that follows from functoriality. Now what about this other one? If we look at this one, you might think that it's similar. Of course, that should have been a gamma. That should have been a gamma everywhere. Sorry about that. Gamma, 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 and gamma, and gamma. So now what we're going to do is this part here where we've got a beta and a delta. So this is, what is it? That's F, and this is F. This is beta F. And the components of beta F are beta at F of x, and this is delta F, and the components of delta F are delta at F of x. Now when we vertically compose these two things, we just compose those. So the components of delta F composed with beta F vertically at x, that's just delta F of x composed with beta of F of x. And we know by the definition of vertical composition of natural transformations, that simply is, by definition, the component of delta composed with beta at F of x. So that's the same as the vertical composite delta beta with an F whiskered onto the beginning of it. So in fact, this interchange law comes from three things. It comes from functoriality of one of the things pointing this way. It comes from the definition of vertical composition, and it comes from naturality somewhere in the middle. Now here's a comment for the more advanced. People who know about weak things know that if you weaken everything, you only get interchange weakly. And that weakness doesn't come from any one particular weakness in your theory. It comes from all three of those things. Now that won't have made any sense. If that didn't make any sense to you, ignore it. And if it did make sense to you, then you can go away and get excited about it now.